Sorry. Okay, so just summarizing for the video, if we have an equation where we have square root of x, so we're kind of okay with that. We get x equals 16. But when x is under the root sign here, it's not something we're familiar with. But it's not that tricky really once it gets unpacked for you. We're saying what root of 8 will give me 2? Well, the cube root of 8 will give me 2, so x is equal to 3. Okay, that's all it's really saying. To put it another way, oops, 8 to the power of 1 on x is equal to 2. What is x? That's another way of looking at it, right? So all of our root stuff can be turned into indices, and what makes this a different problem is that normally when we've got an equation, or up until now, whenever we've had an equation, we've never had to deal with the root sign being, sorry, the variable being in the power. The variable has always been the base or the answer. So x squared equals 16, what is x? 4. Or like I had before, root x equals 4, what is x? 16. It's always been the base. Okay, so it's different. Okay, so let's have a look at some structured examples. We're going to look at solving equations where the power is in the index. I'll come back to that one because, in fact, this one's, it's not that hard, but a bit of preliminary work would help. We know that's going to be 3, but a bit of preliminary work would help. So let's start off with a really simple one, and it's going to be 2 to the power of x. Do you want me to put some formal summary notes together, Would that be helpful? All right. All right, here we go then. Sorry, I just don't tend to do it that often, I should do. It's called Indicial Equations. What I think I might do is I get a bit tongue-tied. Sometimes it's really difficult to express something in the theory, which is probably conceptually better to look at examples first. So let me do a couple of examples and then I'll express the method for your theory book as well. So the examples will go into your summary book as well. Keep going, same method. Yep. The last bit is a real doozy though. It's really quite challenging. That'll make no sense in the video, but I'm leaving it there. So let's have a look at, equations where the variable is in the index. I'm hoping that concept makes sense. So example 1. Let's just say we had 2 to the power of x equals 2 to the power of 12. What would x be? 12. Nothing more to it than that. Is that okay? Okay. Don't write this one down. This is a non-example. If I had 2 to the power of x equals 3 to the power of 12, why couldn't I answer that one the same way? Right. Yep. Bases aren't the same. So you need to have the bases the same. So bases must be the same. I hope this is okay. I'm trying to be a better note taker for students in that often I write a lot and I think example followed by a little statement to bring out what we saw there is enough. If it's not, let me know. But yeah, we'll see how we go. So bases must be the same. So let's have a look at this in example 2 then. 2 to the power of 2x. 2 to the power of 2x equals the square root of 2. Now, we can see there are 2's there, right? But we don't have the same base on both sides. What can we do to make it so that the base is on both, is the same on both sides? Timesing both sides by 2 won't actually help. Timesing both sides by root 2 won't help either, because then I'll just follow through with what I mean. Then I'd have root 2 times 2 to the power of 2x equals 2. That's great, but now I've just got the root 2 on the other side. So thank you. It won't help us. Squaring both sides would definitely work, but I've got a faster method. So squaring both sides is a legitimate method. But, huh? No, because you're squaring the whole of the left-hand side, and the whole of the left-hand side is 2 to the 2x. And then we know from our index laws, so that's where we get that from. But I'm not even suggesting we do that anyway. But you don't square 2 to the 2x, remember, is a notation. It doesn't mean 2 times 2 to the x or 2 times 2x. It simply means repeat the multiplication of 2x times. So it's all bundled in together. Fair enough. The look on your face says, yeah, that doesn't quite make sense, Richard, and fair enough too. But you need to just remember that when we raise the whole of the left-hand side to the power of 2, you need to remember that effectively we're using this rule here. Okay, it's using that rule. We multiply the powers together. Okay, so there's a slightly better way we can do it though, or more efficient. I'll go back to this screen. Look at slide 3. How did I get x to the root of 8? What did I do to that? Henry? If you square root both sides, you're going to end up with the 4th root of 2 on that side, so it's actually getting a bit more complicated. Again, have a look at slide 3 compared to slide 2. Look at don't worry about the fact that it's an x, but what did I do to the x root of 8? How did I rewrite that? That's mutter down the back sounded okay to me. And that confirms what down, I don't know who was muttering down the back there, but yes, you can convert any root into a fraction power. So you can say 2 to the 2x equals 2 to the half. Therefore, 2x equals a half, and x equals 1/4 by dividing both sides by 2. Is that okay with everyone? Yep. So we call this equating powers or equating indices. Sorry? It's not 2.5, it's 2 to the power of a half. So I'd go back and check I'll do it in slide 8 really quickly, but all the theories in previous weeks. So we've got like 2 to the power of 3 is equal to 8, 2 to the power of 2 is equal to 4, 2 to the power of 1 is equal to 2, right? When we do, I'm doing the wrong one, sorry. That's for negative powers. Yeah, really quickly, 2 to the power of a half times 2 to the power of a half is equal to 2. That's the same action as root 2 times root 2 is equal to 2. So root 2 equals 2 to the half. Yep. And so in general, this is not just for you, Josh, nth root of a is equal to a to the power of 1 on n. That's the index law. The nth root of a is the same as a to the power of 1 over n. This is what we did just before surds. The nth root of a is a to the power of 1 on n always. Okay, has that sort of answered everyone's questions for where I got stuff? They're really important questions, so don't keep on asking. Okay, 2 to the power of a half times 2 to the power of a half. Basic index law, same base, add the powers. What's a half plus a half? And root 2 times root 2 is also 2. Yeah, yeah, Josh, yeah. Root 2 times root 2 is root 4. Root 4 is 2. Okay. How do I get here? Okay, now I'm starting to repeat questions that have just been asked. If they've got the same base, then we can do what's called equating the powers. So we've got 2 to the 2x and 2 to the half, so therefore 2x must equal a half. Okay, here's my theory notes. Equating indices or equating powers. Yeah. Who asked that? Violet, it well, you will see more examples where we do that kind of thing in a sec. But the answer is not all the time, but there are plenty of times where you can do it. Hannah. Which we can't do. But surely you can work out what 3 to the power 12 is, and then. Oh, Hannah, I'm not saying you can't work out what x is. You absolutely can. Yeah, definitely. But what is it? Exactly. Even something simple like this, right? It doesn't have to be that hard. 2 to the power of, don't write this down, 2 to the power of x equals 7. What is x? Exactly. Don't go any further. Because we know that 2 cubed is 8. We know that 2 squared is 4. So we know that x is going to be between 2 and 3. It's going to be some sort of decimal number. It's going to be 2 to the power of 1.3 or something like that. 2 to the power of 2.3 or 2.6. I don't know. The truth is that there is a method for doing that. It's called logarithms, and you don't do logarithms until year 10 maths extended. In other words, it's like a year 11 concept. Okay, so no, absolutely legit question, Hannah. But I'm saying if we're going to use the method of equating powers, we can only do that if the bases are the same. Does that make sense? Stella? So what I did is I took root 2, which remember, I'll just do it in blue. So remember that for square roots, we don't write the number in there. So if you just see the root symbol, it means the square root of. And the square root of means there's a 2, an invisible 2 there. And so that's where the half comes from. Yep. Another lovely question. All of these things cement what seems to be weird and hopefully makes it clear in people's heads. Sam? Third, yep. And if it was a 10th root, it would be 1 over 10, etc. Yep. Anything else? Awesome questions. Keep them up. I'll just finish this sentence. So sometimes we have to manipulate. I might just change it to one side of the equation. Okay, so same basis is the key there. Sometimes we have to manipulate one side or both to get the same basis. So while the bases are different, we can't apply this method. Of course, there is definitely a solution for x. We just can't do it using this method. Okay, so equating indices only works when bases are the same. I have to flick to the next screen now, so I'm just checking. Raise your hand if I can't move on yet. Yep, give you another minute. Remember that these notes will go up on Google Classroom, so if I go faster than you, then you can always go to Google Classroom and get them. Or if you're using your laptop so that you can see the screen closer to you, then you can always take a screenshot right now. Okay, the rest of the examples I've got are really just the same theme, really, that I have to manipulate until I get to the same base. I am going to change over now, so apologies for those that I haven't given you enough writing time. So let's take 2 to the power of x equals, yep, oh, sorry, yep, it is. I'm just going to put example 3 there, that's all. You don't have to rewrite it yourself. Example 3, 2 to the power of x equals 1 on 2 to the power of 3. 1 on 8 I've just done, but I've just put it in base format already. So remember, I cannot solve this until I've got base to the power on left, same base to the power on right. Now, it might look like I've got that, but I don't, because the right-hand side is not base to the power of, it's 1 over base to the power of. Who can tell me what we could do to fix that? This is why your index laws are really important. Henry? Fergus? Make it a negative index, right? So that means 2 to the power of x equals 2 to the power of negative 3. And now it's really simple. What's wrong? I thought that x underneath, I thought that 3 underneath 1. That one? I swear I have never had this much blowback about my writing skills before this class. Yes. There is no half there. There's 1 on 2 cubed. Who asked that? There is no half there. There is 1 on 2 cubed. And 2 cubed is just 8. So you're seeing an 8th on the right-hand side, but written as 1 on 2 to the power of 3. Now, again, really quickly, because this is all in the notes from 2 weeks prior. If I have 2 cubed, I get 8. If I have 2 squared, I get 4. If I have 2 to the power of 1, I have got 2. All I'm doing is I'm going down by a half each time. If I go down 1 more, I've got 2 to the power of 0. 3, 2, 1, 0. That would be equal to 1. That's also consistent with multiplying by a half. So if I go down 1 more, I would get 1/2. 1 times a half. Okay? If I keep on going down, I would get 2 to the negative 2, and that would be a half of a half. What would that be? A quarter, or 1 on 2 squared. And if I kept on going down, I'd get 2 to the negative 3, which would be a quarter times a half, which is an 1/8, which is equal to 1 on 2 cubed. So can you see how the pattern here is that as I go into negative powers, I'm effectively going 1 over 2 to the power of the positive power. And that's how it works. That's how negative powers work. They turn into a fraction number. Not a fraction power, but a fraction number. Okay, example 4. Just throwing lots of different examples, and every time I throw you a curveball, you're going to ask me all those beautiful questions that you've been doing so far. 2 to the power of x equals 16. We've got 2 numbers here. 2 and 16 do not have this, they're not the same base. So I can't equate powers. Even though that's 16 to the power of 1, I can't say x equals 1. That doesn't make sense. What can I do to make them the same power? Raf? Great, done. Perfect. See what I mean? So you need to know your powers. So if you're given 2 to the power of x equals 16 in a test, you need to know, well, you just need to know that you need to get 16 as 2 to the power of something, and then you just need to ask yourself, what would that be? 2 times 2 is 4, times 2 is 8, times 2 is 16. Even better, just know that 2 to the power of 4 equals 16. Okay, any questions? Great. Do keep on asking those questions, though. Only if they're relevant, of course. Don't say, like, what's your favourite colour, Richard? Yes, Charlie? I'd know your powers of 2 up into 2 to the power of 10, I suppose. They're not that hard to work out, though. 3 to the power of, at least 3 to the power of 4, which is 81. 4 to the power of 3 would be reasonable. I don't think it will be a calculator test, actually. I'm happy for you to have a multiplication sheet, though, a times table sheet. But I don't think, because there's too much that could be easily done with a calculator that would circumvent us testing your, like if I said what's 2 cubed plus 2 to the power of 5, you could just do that on your calculator. Whereas what we want is 2 to the power of 8, because you know to add the powers. Do you know what I mean? I think it'd just be a bit too much of a lean on. But yeah, I'm happy for a times table sheet. Example 5 is thusly. 2 to the power of 2x minus 1 is equal to 2 to the power of x plus 3. This is no more difficult than you have done before, but now you've got a linear equation you have to solve. We equate the powers because the bases are the same, so I can go straight to equating powers. But if your equation solving is a bit weak from here, then that's what you'll need to practice. I'll do it quickly because I think it's fairly straightforward. And if it's not, that's on you to practice that. So I'm going to have x minus 1 is equal to 3, and therefore x is equal to 4. I can go back and check. 2 times 4 is 8 minus 1 is 7. So I've got 2 to the power of 7 here. 4 plus 3 is 7. I've got 2 to the power of 7 here. So left-hand side is definitely the same as right-hand side. Questions? Example 6. 2 to the power of x. Sorry to be picking on 2s, but it's just, if I keep the numbers low, it makes the rest of it you're just understanding the power bit instead of trying to come up with harder numbers, I suppose. Equals 4 to the power of x plus 1. Damn. Different bases, and they've already got power, so what are we going to do? Sam? Great. That's all I need to hear. 4 equals 2 squared. So that means we can replace 4 with 2 squared. Watch this. Keep it in brackets because I'm replacing the 4 with the 2 squared. And then x plus 1. And then now we're going to use the rule that if I've got a power inside the bracket and a power outside the bracket, what do? Times them together. So now I've got 2 to the power of x equals 2 to the power of 2x plus 2. We've got to expand. 2 times x is 2x. 2 times 1 is 2. We've got to expand. And now we can say x equals 2x plus 2. And we can say that negative x equals 2. So x is equal to negative 2. Boom, boom, shake the room. Should work. 2 to the negative 2 on the other side. Negative 2. 4 to the negative 2 plus 1 is 4 to the negative 1. Yep, that works.
Wait, how did you get from like x equals 2x plus 2 to x equals 2?
Took x away from both sides to start with. So x take away 2x is negative x. So negative x equals 2. But you don't want to know what negative x is. You want to know what x is. So you times both sides by negative 1. That gives me x here and negative 2 there. Sure can. Is that okay? Another way I could have done it, but it'll just make people confused the other way, is I could have taken away x from both sides, and that would have got me 0 equals x plus 2, and then take 2 away from both sides to get x equals negative 2. Either other way. One more example. Oh, yeah, gee whiz. This is not good. Example 7. Two to the power of x minus 1, I think. X minus 1 plus 1 is equal to 9. Three numbers there. 1's okay because I could make that 2 to the power of 0, right? So whenever you see 1, think, oh, that's any base, really. But 9 is not a power of 2. Harry, you're a legend. Harry, perfect, legend. But if we take 1 away from both sides. So the other thing to point out too is that it's base to the power equals base to the power. It has to be like that. If it's base to the power plus something, that's never going to work. Okay, well done, Harry. So 2 cubed. So now we've got x minus 1 equals 3 and x equals 4. Yeah? See how there were huge numbers of questions at the start and now they're just really fine questions now? So it was really worth asking those questions at the start. Any questions? I'm going to give you a whole heap to do now. So the 2 to the x minus 1 had to be there because it was. We took a 1 away from both sides. I didn't write in, but I hope it made sense to get 8. But the only way I can set x, I can solve for the index is by changing 8 into a power of 2, and 8 is 2 to the power of 3. So I've changed 8 to 2 to the power of 3, and now I can say this index must be equal to this index. This is the first time I can say x minus 1 equals 3. Before then, I didn't have the same base. This is just 2 to the x minus 1 equals 8 to the power of 1. Is that okay? It's okay. Maybe practice will help make it solid. Yeah, okay. Any other questions? So you're okay with getting to that point? Multiply both sides by -1. I need to do that because I'm not interested in what negative x equals. I'm interested in what x equals. So whenever you're left with a negative variable, multiply both sides of the equation by -1 to switch the signs around. Times both sides by -1. You know what? If you don't like that, if you've got negative x equals 2, I can add x to both sides. Hello, long time no see. I can add x to both sides, and I can take away 2 from both sides, and that'll basically make it switch positions and also switch signs. So there's lots of ways you can slice that little tomato. Yeah.
How did you know that, like, on the third line wasn't like the last line?
Huh? This line?
2x minus plus 2, same as x minus 2. Like,
Are you talking about this line here?
No, the one below.
This one?
Yeah.
Why wasn't it the last line?
Yeah.
Because there's an x on both sides of the equation. Remember, the name of the game is not to just to get something that has x on the left and something on the right. The name of the game is to find a value for x. I have not found a value for x. You know what I mean? It's like one of those things like, how do you define a circle? Well, a circle is a circle. You can't, that's not a definition of a circle. You can't use circle to define circle. You can't say x is defined as being twice x plus 2.
Yeah.
Yeah. So you have to keep on going until you've got x by itself. Standard OP, right? Standard operating procedure is that if you've got x on both sides of the equation, eliminate it from one side. So my choice was to take 2x away from both sides. That left me with 2 on the right, and x minus 2x is negative x on the other side. So that's standard procedure for variable on both sides. Okay, moving on. Back to here then. 8 to the power of 1 on x equals 2. What I could have done is I could have gone, this is like overkill, right? You'd never do this really. But I'm just saying, to show you what I mean, I could have said 8 is 2 cubed. Sorry about the red. And 2 is just 2 to the power of 1. So I've got 2 to the power of 3 on x is equal to 2 to the power of 1. And so that means that I would have 3 over x is equal to 1. by equating powers. Multiply both sides by 3. And I've got x is equal to 3, or 3 is equal to x. So, I wouldn't do that. I'd just go, no, it's 3. Because I know the cube root of 8 is 3, or is 2. I just do that. But I'm just saying it is all consistent. Our work with roots, our work with powers, they are all consistent within each other. All right, I'm going to be quiet now. Well, not quiet. I'll stop the video, but I'm going to hand out 2 worksheet sets, and then I'm going to let you work through them at your own pace.